J plus I. J cross I. J is not. Yes, if J cross negative I is I'm sure that I cross J is K. J is like so that I guess right. I would J is K. Do the opposite is negative. And then if you have a negative, then I can again. It only gets complicated when you start doing like J and K and I and J. How do I do that? You do this because we cross product different things. Well, I just make out the table thing. You know, like we have to do like undergrad code, like other the matrix. I just compare that. I've never done it about for like. Like what's the equation for you? No, just don't. I like K. I is minus negative minus A plus and if you can just plug your, you'll know what you can. There'll be a lot.
Okay, so any questions before this slide? So today we actually need to finish this chapter. Okay, I don't know if we can actually go through all the example or not, but we'll try. Okay. And one thing I want to actually make an announcement is that we are going to post the partial credit assignment for midterm 2 today. So the deadline will be, I guess, next Tuesday. By the time that you don't have access to your midterm 2. Okay. So rules will be the same, and just make sure you actually turn in your partial credit assignment in time. Okay. So any question for that? Okay, so if not, then let's get back to this chapter. Okay, so on Tuesday, we start to introduce the concept of entropy, right? So entropy, we say that's actually the ways, if your system has more ways to distribute your energies, then the specific process have higher probability to occur. Okay, so that's actually a basic concept we went through, and then we tell you if I give you a molecule, okay, how to actually predict which one has larger entropy, right? So we start to talk about the phase matters, right? So gas phase always has the largest entropy compared to the liquid and the solid. Okay. And if all the things are in the gas phase, then the things we have to compare is actually how complicated that molecule is. The more complicated molecules don't give you a larger entropy. Okay. So larger atomic molecules will give a higher entropy than the single atomic molecule. Okay. And then it's actually the same, if you have the same number of atoms, then start to compare who is actually heavier. So that's pretty much the things we went through in the previous lecture. Okay. Then today what we're going to do is actually to tell you another new very important concept for thermodynamics is that in order to actually define the entropy of certain things, okay, you need to actually understand. We create this terminology for system, okay, and in the eye of scientists, okay, if we have a specific target, we call it as our system, and anything else will be surrounding, okay, and then the things that the system plus your surrounding, we call it as universe. Okay, so that's just the terminology that you have to know. Okay. And this is important because when we actually look at our chemical reactions, how do I know it is going to happen spontaneously or not? Everybody actually have an idea about what it means by the spontaneously. It's going to occur naturally. Okay? For example, H2 plus O2 will produce H2O. Okay, so this thing will happen spontaneously. Okay, so in this case, what is your system? Okay, so this H2 plus O2 they give you H2O. Okay, so for this specific reaction, what is your system? It is actually the beakers or containers. Inside you have your H2 and O2, right? So those are your system. Okay. So what are surroundings? Is anything but less small containers is your surrounding. Okay. So the reason you need to actually make this distinction very clear is because remember when I say chemical reactions, we typically heard this term endothermic or exothermic, right? So exothermic means actually you're going to release your energy to where? To surrounding, from where? From your system. Okay, so it's very neat, it's actually very neat to actually have this idea very early on, because later on we are going to learn a very important things. The ultimate parameters that scientists will predict whether a process is a spontaneous or not is actually using this term called the delta S universe. Okay, and then if what I say is actually if your delta S universe is positive, then the process you are looking at will be spontaneous, meaning the reactor will go to the product side. Okay. So what does this mean? So this means when the things happen from one side to the other side, right? The things you compare is actually before and after. Okay, so after it happens, you have certain status, you have certain energy. Before it happens, there's actually another set of energy turnover there, right? Then compare the two and see whether this is actually a feasible things to have. Okay. But delta S is entropy terms, right? It is not really energy, right? It is actually more like the probability or ways that you can actually store your energy. Okay. So what you want to have is that after this thing happens, you want to have more ways to store your energy. Okay, that's actually your final state after your initial state. You actually have more ways to store energy, then this thing will become possible. Everybody get this idea? So rephrase again, okay, so you can actually understand physical meanings. So we want to actually always want to have a condition that you have as many possible ways to store your energy. Okay, and this actually for the reaction to occur, okay, you have the initial and final, right? If this is going to be spontaneous, then it's actually your final state must have more ways to store your energy. Make sense? Everybody follow this? Okay, so how do you know it is? Okay, and these things, of course, you can look at your system alone. Okay, but that actually doesn't actually going to give you the answer because energy flow between your system and surrounding, right? What you have is actually overall, both your system and both your surrounding have more ways to store your energy than that thing. That specific process will actually very high probability to happen spontaneously. Okay, so that's actually the main reason, physical reason behind the delta S universe must be positive. Okay, so you can see I also put another term called delta G, right? So what is delta G? It's free energy. Okay, so delta G was actually connected to the delta S universe. Okay, by the next equation we list here. Okay, so let's go through the things I wrote here quickly. First thing is actually, I hope by now you should know that delta S universe is actually the term that scientists use to predict whether a reaction is going to be spontaneous or not. Okay, and it's actually composed of two terms, right? Delta system and then delta surrounding. Okay, so the way system and surrounding is taught is using what? It's using energy. It's using heat. Okay, so if you let's actually heat transfer from your system to your surrounding, you can actually rewrite these things. Okay, so you keep your system the same. Okay, let's say you have that reactions, it's exothermic. Okay, so you can get the delta H. Okay, so once I produce the delta H, it's going to go to your surrounding, right? So it's actually the same amount, but to your surrounding, it's going to get that delta H. Okay, that means actually when you write these things, the sign will tell you the amount that your delta H get will be the same quantity. Okay, but it's actually your system is actually losing the delta H that goes to your surrounding. Therefore, you put the negative sign in front of it. Okay, and then we define entropy as the energy divided by the temperature. Okay, so why? This is actually a very interesting way to define the entropy. Okay, so your entropy is actually delta H over T. Okay, so more general way is actually Q over T. Okay, so that's actually how you define your entropy, right? So what does this mean? So what's actually in your numerator? Heat, right? Heat is a form of energy. Okay? So what is T? T is in your denominator, right? So remember what we say in the beginning, we say the entropy represents how many ways you can actually deposit your energy. Okay, so the way you write this is means that the T represents how big the energy dispersion is. Think about this. And I'll give you a very simple example. Okay. Let's say you have 100 volts represent your energy. Okay, represent your heat. Okay, and the T is like the size of your basket. Okay, so if your T is really big, let's say you have a very big basket, right? Then the way you can actually store and fill the basket using the same energy will be actually very big. But if today the basket is very small, then you will need to actually have multiple baskets to consume all the energy that you have. Okay, so the number of baskets is actually a representative of how many ways you can store your energy. Okay, so if you have smaller T, so the same amount of energy, then you have more probability to actually store the energy. Okay, so let's actually a basic fundamental reason why scientists write is Q over T. Okay, this kind of represents how many ways you can actually store your energy. Okay, the larger the better. Okay. Does anyone follow what I say? Is this actually making sense to you? I guess this is actually your first time to hear all this theory. Okay, the things I say will be repeated again if you take thermodynamics, okay, in your senior year. And that's actually a fundamental reason. Okay. But if you don't understand what I say, that's fine. Do remember this equation. That's something that's actually more relevant to you. Okay. So once you write these things, then you can actually multiply this negative T on both sides. for your delta S universe. So you end up with this equation. Okay, then we define this negative T times your delta S universe as your delta G, the Gibbs free energy. Okay, that's the definition. Okay, and it's going to compose negative T delta S system plus your delta H. Okay, right now, the things they want to do this is because right now your delta S and delta H, they are the information they can get from your system directly. Okay, so you can just look at the system now without worrying about your universe. Then you can predict whether things going to happen or not. Okay. And then because your delta G was defined as negative T times your delta universe, the delta S universe is always positive. Temperature is always positive. Therefore, that means actually if you have a spontaneous process, your delta G will always be negative. Okay. So up to this point, the things that we should really know is that your delta S is composed of these two terms. Okay, delta S system plus delta S surrounding the given delta S universe. Okay. The other thing you need to know is actually your delta G was defined as negative T times delta S universe. And most importantly is this. This is always true. Your delta G is going to be equal to your delta H minus T times delta S. So that's actually one of the most famous equations for thermodynamics that put together how your entropy, and free energy are connected with each other. Okay, so we're going to do some questions for this. Okay. All right, so the next things that we need to actually learn for this chapter is actually, if today I give you a table, I give you a chemical reaction, how I'm going to use the information in the table to calculate the delta G, delta H, and delta S for a given reaction. Okay, you guys actually practice a lot for the delta H calculation in Chem 1. Okay, and what we're going to do today is actually we're going to explain that so you know how to calculate your delta G and delta S. Okay, but basic idea is always very simple. If you want to calculate the delta G of a chemical reaction, it's always product minus reactant. Okay, so it's always product minus reactant. Okay, so what you need to calculate is actually the summation of all the delta G naught of your product times its coefficient. Okay, coefficient I times the, we're going to use this term called the delta G naught formation for every single product that you have. Minus the summation coefficient times delta G naught formation of your reactant. Okay. So this equation is always true, and you will apply to your delta H and delta S as well. The things that you need to change is change the G into H or change the G into S. Okay, so calculation-wise is exactly the same. Okay, so those are the things that we should know first. Okay, so let's go through a few questions so that you have a better idea about how to use this. Okay, so this question says for a combustion of acetylene at a specific temperature, 2C2H2 plus 5O2 that give you 4CO2 plus 2H2O. Calculate delta S, not universe. Given that delta S system is certain value, delta H is certain value. Okay. So what are the keywords here? Okay. So let's do our 2D papers. Okay, Q. You want to know your delta S not universe, right? And then the data that you have is your delta S not system. Negative 194.6 joule per K. Delta H not system equals to negative 2511.2 kilojoules and make it become joules. Okay, so I multiply 1,000. Okay. And then the temperature is 298.15. Okay, so here you see this delta S system, delta H system, right? So previously we actually only talked about one equation contain both terms, which is delta G equals to delta H minus T delta S. Okay, so in this case, you know, this one is here, temperature, and you have delta S. Let me actually, from the given information, the quantity they can calculate what? Your delta G, right? And then you also need to know delta G is equals to negative T times your delta S universe, right? So that means that if you put these things, you substitute this guy with this term, then you will be able to calculate your delta S universe. Okay, so that's the basic idea how you do this calculation. Okay, so let's just put the number in. So negative T times delta S universe is going to equal to delta H minus T delta S. Okay, so I'm going to divide the temperature first on both sides. So I know my delta S universe is going to equal to negative delta H over T plus your delta S. So that's negative delta H is this value, right? Negative 2511.2 times 1,000 divided by your temperature, 298.15 plus your delta S. System is negative 194.6. Okay, so by doing that, you can get your delta S universe is going to equals to 8228 joules per K. Okay. So let's recap this quickly. Okay, so here actually tests you two things. First thing is actually, do you know the definition of delta G? How it's actually related to your delta S universe? So you must actually remember delta G is going to equal to negative T times your delta S universe. Okay. Second question that you have to memorize is that delta G is going to equal to delta H minus T delta S. Okay, so by using these two equations, you will be able to solve your delta S universe without any problem. Okay, so that's how you handle this question number 2. Number 3, you must actually see this top table in your CHEM1312 when you calculate your delta H. Okay, so we're going to do similar things here. Okay, so let's read the question first. So in these questions, it tells you the temperature is actually 298, right? And then it gives you a bunch substance. But the things you want to look at is actually here. There are actually 3 columns. One is your delta H knot formation, delta G knot formation, and then the entropy. Okay, so those are the 3 things that you need. Okay, so then it says you want to, so for the combustion of hydrogen of these specific reactions, they want to calculate the delta S naught, delta G naught, delta H naught for this reaction. Okay, so the way you do this is actually very simple, right? Let's start from the delta S naught first. Okay, so what you need to do is actually you need to do this summation of the coefficient times your entropy of your product minus summation coefficient times your entropy of your reactant. Right, this is all you need to do. Okay. That means what? For these specific reactions, this is your product, right? 2H2O in the liquid form is your product. Okay. Pay close attention to the phase because different phase give you different values. Make sure you actually identify the correct terms. Okay. So what this means actually, it means actually a coefficient is actually 2. You want to know your entropy of H2O in the liquid form. Okay, so let's say what you're going to have for the first term. The second term, okay, you have 2 reactants, right? One is H2, gas form. One is O2, gas form. Okay, so to actually first find out the entropy of your H2 gas form multiplied by its coefficient 2 here, plus the entropy of your O2 in the gas form multiply its coefficient. You did not write anything, right? So the default will be just 1. Okay, so it's 1 times that. Okay, so this is actually the equation that you're going to use. Okay, so once you understand this, then you come back to here, come back to your table. First, to find out the entropy of your H2O liquid. H2O liquid is right here, right? Entropy term will be this. Okay, so you need to know how to actually identify the numbers. So you have equals to 2 times 69.91 minus 2 times the entropy of your H2 gas. So it will be this number. So 2 times 130.58 and plus 1 times the entropy of O2. O2 is here, so use this number, 205. Okay, so once you do that, you can actually find out your entropy will be negative 326.3 joules per K per mole. Okay, so let's see your delta. It's not for the reaction. Okay. Any question for this? Is this clear? Okay, so that's how you do your delta S. How about your delta G and delta H? It's exactly the same process. The only thing you can change is that When you ask for your delta G, then you use this column. Okay, when you ask for the delta H, you use this column. Okay, but calculation is exactly the same. Okay, so let's do this quickly. Delta G will equals to 2 times H2O. Delta G is the second one. Okay. Negative 237.13 minus 2 times. Okay, so here you can see the delta G now for your H2 and O2, they're actually all 0, right? So 2 times 0 plus 1 times 0. Therefore, your delta G now will be negative 474.26 kilojoules per mole. Okay, and then you can do the same for your delta H now will be 2 times H2O is negative 285. Negative 285.83 minus 2 times 0 plus 1 times 0. That's negative 571.66 kilojoules per mole. Okay, there will be your delta H now. Okay. So you can see these questions a lot in your homework, in your quiz, in your midterm. Okay, make sure you can do this. It's very simple. Okay. Any questions? Okay, so I think that's the things we went through using the concept we learned. Those are the questions that we can do. Okay, so right now we actually need to learn a little bit more. Okay, so now come to actually some interesting parts. Then you start to try to use your delta G to predict how the reaction is going to move. Okay, so previously we say if something is spontaneous, it implies that it's going to move from your reactant side to your product side. Okay, and in order to make it to happen, your delta S universe must be positive or negative. Positive. Your delta G must be negative. Okay, this looks like opposite sign, so be careful. Delta S universe has to be positive. Delta G has to be negative, so that you can ensure the things that can move from your reactant side to your product side. Okay? So now, if I tell you there's actually a reaction, its delta G is positive, how the reaction direction going to move? It will move from the product side to the reactant side. Okay? So this is actually a very important concept you must have. If the delta G is negative, move to the product side. Delta G is positive, will move to the reactant side. But if delta G equals to 0 at equilibrium, okay, critical concept you must have. Every time you see a portion say a system is at equilibrium, that means your delta G will equal to 0. Okay, it's always true. Okay, so you must actually have those concepts. Okay, so with this being said, the other things you must know is that you should see that the temperature that gives you the delta G equals to 0. Okay, that is actually the temperature that you can easily change your spontaneity. Okay. If it become positive, then you move to the reactant side, negative move product side, right? So that delta G equals 0 is actually the special point, okay, where the change of lab, okay, that's the temperature that your system is actually equilibrium. Any deviation of lab will actually move to different directions. Okay, then it's actually your spontaneity is going to change at less specific temperature. Okay, so that's actually the first thing that you should know. Okay, second thing, how do we actually connect our delta G to the equilibrium constant K? Okay, so here we need to have actually really good understanding the difference between delta G and delta G not, meaning the superscript 0. Okay, so you often see these things in your textbook. See these two? They're actually not the same. Okay, so what does this little 0, little not mean? Standard condition, right? What does it mean? That means your reaction is conduct under 25 degrees C, 1 Yen, and 1 N of the solution. Okay, so why do we want to have the standard conditions? Because in the past, scientists want to create a table. Okay, so if you want to create a table and test everything under the same condition. Okay, so we define the standard condition is actually specific temperature, specific pressure. Okay, and then specific concentration. Okay, so then let the reaction to occur, right? So I have this thing set up, then let the reaction occur. What's the end point of the reaction? When would you say a reaction actually comes to an end? At equilibrium. Okay, so that means you're going from somewhere, okay, where you set it as a standard condition. Okay, then you let the reaction to go, and you observe that how the heat changes. And at the very end, you're going to hit your equilibrium state, right? So the energy difference between those two is a specific quantity for a specific reaction. Okay, but you can always define that quantity as your delta G naught or delta G 0. Okay, and that energy is going to be related to your equilibrium constant K, because eventually, no matter where you start, okay, it's going to hit the equilibrium after reaction ends. Therefore, they do a lot of observation and eventually come to this conclusion. And then they want to define, okay, to compare between different substances. Let's compare how far away their delta G naught is, okay? And then they realize this one can be correlate with the equilibrium constant K, multiply a constant R in the temperature T. Okay, so delta G naught is directly related to your equilibrium constant K. Okay, of course, there's a prefactor R and T. Okay, so that's actually how scientists actually end up with. Okay, so if I can actually measure the energy changes under standard condition, okay, and then number is going to relate to the equilibrium constant K of the specific reaction. Okay. So if you look at this equation, they say you have a spontaneous reaction. They say H2 plus O2, that give you H2O. Okay, you probably have a negative delta G naught is negative something, right? They say just random number, negative 10. Okay, they say that's actually the number you got when you do the measure. Okay. Okay, so this is just a prefactor, right? Next RT is just a prefactor. Okay, So the negative sign will cancel out, right? So the larger or more negative your delta G naught is, your K is going to be larger. Okay, that is actually energy-wise, is actually in favor. Okay, you want to actually get this in flow. Okay, it actually gives you a lot of energy after you complete your reactions. Then your K, your equivalent K, will be actually big. Okay, so that's actually quite implied from this simple equation. Okay, so here defines that your delta G naught is associated with your equilibrium constant K. Okay, and that's actually you define a very well-defined state. Okay, previously there's actually a concept we mentioned. It's called chemical quotient Q. Right? So the difference between K and Q is that K is the system at equilibrium, right? Q is actually the system at any different states other than equilibrium. Okay. So how do you actually write the energy, the delta G, for the states that's not at equilibrium? Okay. It turns out it's actually very, very similar. Okay. So if you have any as a species at a random state, not at a standard state, okay, you can actually still relate it to your delta G you measured. Okay, so your delta G is going to relate to your Q in this way. Okay, so you can think about this is actually at equilibrium, right? This is actually at any condition. Okay. So, everyone fine with this argument so far? This chapter is a little bit abstract, but you know, I have to stay with me. Yes. So what I'm trying to say is that if the amplitude, okay, everybody actually recognize amplitude, and then the sign in front of it, that two different things. Okay, so if there's a negative sign in front of it, the negative sign can cancel out, right? The larger the amplitude will give you a larger K. Okay, larger K is actually, we always say the K is actually a ratio between what? Product over reactant, right? So larger K is actually you're going to form a lot more product once you reach equilibrium. Okay? Does that answer your question? Yeah. Okay. I mean, the things we're talking about is actually really beyond the scope of this class. But I think it's actually, you know, the physical means it will make a lot of sense. Okay. But so we can actually write we can actually associate your K with your delta G naught, Q with your delta G. Okay. But we actually write out an equation. Okay. This is actually for one single species, right? But when we write out an equation, it's actually a mixture of multiple species. Okay. So if you actually look at an equation, chemical equation, when you calculate the delta G of that reaction is the total G of your product minus the total G of the reaction. Compare that from the beginning to the final. There's actually a lot of delta here. I hope everyone can see this. Okay. The first one is actually the energy difference between your reactant and product. Second is actually when the reaction occurs before and after. Okay, so every time you see this delta G equals 0 for the reaction, then it's actually the overall differences for your final state minus your initial state. Okay, then it's actually once you reach equilibrium, you have a final state, right? compared to your initial however status that you have over there. Okay. So how do you actually write out that delta G for the reaction? Delta G for the reaction will be your final state, will be your delta G final minus your delta G initial, right? So what is actually your final state will be? We just say the rational confluent end must reach equilibrium, right? That means the first term here will be actually your delta G naught, right? Your delta G naught is actually the term that indicates this term how about it's associated with the equilibrium constant K. Okay. How about initial? Initial will be this, right? Just your delta G. Okay, so you can actually rewrite this. This will be negative RT natural log K minus negative RT natural log Q. Okay, so you have negative RT natural log K plus RT natural log Q. They will be actually the delta G of your reaction. Okay. All right, so that's actually what I'm trying to write here. Okay, negative RT natural K plus RT natural Q. There will be the delta G of your reaction. Okay. Okay, so inside your the question I'm going to encounter for this chapter, okay, it will always ask you, okay, if I give you a delta G naught and predict your K is larger, small, or equal to 1. Okay, because you know the delta G naught is a representation of your equilibrium constant, right? The delta G naught is actually associated with your equilibrium constant through the negative RT natural log K. Okay, so let's talk about these three things. Okay, so if your delta G naught is positive, okay, that means your negative RT natural log K has to be negative. Okay, R is just a constant, so it's not going to affect your sign. Temperature is always positive. Okay, therefore you know your natural log K has to be positive or negative. Positive, right? Everybody follow this? That's right. This should be positive here. Because this equals to that, right? Negative RT natural log K. Therefore, your natural log K should be negative. Right? Therefore, your K will be smaller than 1. Okay, so this is actually how you actually get to that conclusion. Okay. Any questions? and that's confusing. Okay. What if your delta G is 0? If your delta G naught is 0, then what's the K? 1, right? Because R and T is not 0. So that is actually your initial K has to be 0. Therefore, your K has to be 1. Okay. And then if your delta G is negative, that means actually your, okay, so let me write these things. Okay, so this just some basic mathematical operation. But if you know how to do these operations, then you can actually, based on the delta G 0 values, you can actually predict your K is going to be larger, equal, or smaller than 1. Okay, so this is actually one thing that you probably see in your quiz, I believe. Okay, so that is actually how you solve the problem. Okay. And the other thing, so this one is actually simpler conceptual-wise. Okay, delta G of your reaction. So if your delta G is equal to 0, that means you are at equilibrium, right? That means actually Q and K, they are going to equal to each other. Okay. If your delta G is negative, that means things is going to happen spontaneously. Okay, so I write these things opposite. If your delta G is negative, I guess I'm fine. Okay, so if you look at this, that means actually the first term should be dominant term. Okay, therefore your K should be larger than your Q. Okay. If your delta G is positive, that means the second term dominant than the first term. Okay, so then your Q is going to be larger than K. Okay, so I know it sounds, okay, it is not very straightforward for you to actually understand this, but remember these rules will help greatly for your problem solving for this chapter. Okay, so that's pretty much all the concepts that you will need to know. Let's do some more questions to actually strengthen those concepts. Okay, so this question says a particular reaction has delta H naught value of negative 10 kilojoules and delta S naught of negative 500 joules per mole per K at 298 K. Assuming delta H naught and delta S naught doesn't really change with temperature, determine the temperature in degrees C at which the spontaneity of the reaction changes. Okay, so these questions, this is actually the part that you want to actually pay attention. Okay, because that's actually a part that most students feel confused. Okay, so we just mentioned that If your delta G is positive, move to the reactant side. Negative, move to the product side, right? In between is at equilibrium, meaning that your delta G will equal to 0, right? And that temperature is a temperature will indicate your spontaneity of the reaction can change. Okay, so what this means is telling you, I want to know what's the temperature. Okay, so let's what it really means. Okay, so you have to translate that sentence into the temperature at equilibrium. Okay, so let's write our QD pack quickly then. The things we want to actually know, the temperature at equilibrium, right? Data you have is delta H naught equals to -10 kilojoule, right? Times 1,000. So for this chapter, you are going to see the delta H is always expressed in kilojoules. Okay, but the calculation should always be done in joule. So always multiply that back. Okay, when you do your calculation. Your delta S naught is -500. It's actually going to be joule per mole per K. Okay. So the equation that connect these two is delta G equal to delta H minus T delta S. Okay. Because we know at equilibrium, your delta G is going to equal to 0, right? Delta H is -10 times 1,000 minus the temperature that at equilibrium you want to solve that. Delta S is -500. Okay, therefore you know your temperature will simply equals to -10,000 divided by -500. This should be 20K, okay? But you want to know the temperature in degrees C, right? Minus 273, then you get the temperature is going to equal to -253 degrees C. Okay, so this is actually how you solve this problem. Okay, yes. So in the very last sentence, it says what temperature the spontaneity of the reaction going to change, right? This highlight sentence. That sentence actually, you have to translate that into something that you can calculate. Okay, so we just say at equilibrium, your delta T equals to 0. Okay, positive move to a reactant, negative move to a product side. Okay, so you know at equilibrium, that is actually temperature that the spontaneity is going to change. Okay, so from there, you transfer that sentence into temperature at equilibrium is actually your target. Therefore, you know you have to solve for T. Okay, and this is actually at equilibrium, therefore, that part, you write delta G equals to 0. Right, and then plug in the delta H and delta S and solve for the T. Okay. Any question for this? Okay, if not, the next question is basically exactly the same. I actually remove it. Okay, that's fine. This will be the next one. Okay, so this is also another type of questions you are going to see a lot in this chapter. Okay, so we sort of actually go through these things before, but in the past we actually calculate the new equilibrium constant. But here is actually, they want to calculate the delta G, delta H, and delta S. Okay, so calculation of this delta G, delta H, delta S is actually a lot more straightforward because it's purely addition and subtraction. Okay, so It says you have three data. Okay, so these are the three equations. Each of them has its own delta G naught. Okay. You want to actually determine the delta G naught for a target reaction. So that is actually your target. Okay, so what you will need to do is actually you need to rearrange. They say this is actually your equation set. Okay, you have three equations, right? You need to actually rearrange, okay, maybe multiply some numbers for the equation within your equation set. So that when you're adding up, you go to your target equation. Okay, so this is actually your target. Okay, so that is actually a basic idea. Okay, so let's do this. Okay, that's your Q data. You have three equations, right? 2NO plus O2. That give you 2NO2. Delta G equals to -73. Let's say this is our equation number one. Second equation, N2 plus O2. That give you 2NO. Delta G equals to 178. Equation number two. And then 2N2O plus becoming 2N2 plus O2. Delta G equals to -202. Equation number three. Okay. You want to actually do something for this, but in the end, you want to have N2O plus NO2 that give you 3NO. Right, so that's your target. So the way you solve this problem is actually first, look at your target equation. Okay. How many reactants you have? Two, right? Which two? N2O and NO2, right? That is actually when you rearrange the equation in your equation set, N2O and NO2 should present in your reactant side. Okay, so that's something that you must do. Okay, so let's start from this. First, N2O, right? So that's actually only places you can find your N2O. That means actually you're going to use that equation. Okay. And N2O for the specific equation is already in the reactant side, meaning it's at the right location. You don't do it your chemical reaction. Okay. However, they are different, right? Because the equation 3, the coefficient in front of your N2O is 2, right? So you cannot just use it before you actually adding up. So what you do is actually first divide the whole equation by 2. Okay. So I'm going to divide this equation by 2. Divided by 2. Therefore, I have N2O becoming N2 plus 1/2 of O2. What happened to my delta G? Yeah, it's cutting half. Okay. For your delta G, delta H, delta S, they are so-called extensive property. That means if you actually divide by the coefficient by a certain amount, those quantities will divide and decrease by the same amount too. Okay, since you divide by half of the whole equation, then your delta G is divided by 2 as well. Okay, so go from -202 become -101. Okay, let's call this section 3 prime. Okay, so you solve the first part. Next one, you want to solve the second one, right? NO2. Which equation has NO2? Only first equation, right? Do you need to actually do anything? What do you need to do? You have to flip it and then divide by 2. Okay, so that's what you really need to do. Okay, so we're going to do that. So like if you flip it and divide by 2, you're going to have NO2 becoming NO plus 1/2 of O2. Delta G is going to equals to, since you flipped it, right? So negative 73 now become positive 73. Okay, and then you divide it by 2. Therefore, you have, okay, so there will be your 1 prime. All right. So up to this point, you're taking care of your reactant already, right? Okay. Then what you will need to do is actually you try to add the equations up. Okay. So the things that remain is this and this two, right? And then when you add these 3 equations up, you'll realize that something is going to cancel out. Have O2 plus have O2. That give you just O2, right? This and that is going to cancel out, right? N2 is going to cancel out. Okay. Therefore, let me do that. And the things that remain is actually your N2O, NO2. There are 2 NO, 1 NO. In combined, you have your 3 NO. Okay. That means the new delta G of this reaction will be simply equal to the delta G of your equation 2 plus delta G of 1 prime plus delta G of your 3 prime, which equals to 178 plus 36.5 plus negative 101. Therefore, your N now with your delta G is going to equals to 113.5. It's joule or kilojoule? It's joule, yeah. So that will be actually your answer. Okay. So we're going to see these type of questions, right? So the things that you should actually start is really first focus on your target equation, starting from there. Okay, make sure that your reactant is actually on the right side. Okay, and then make sure the coefficient was actually done properly. Okay, and then eventually when you get up, all the other things will cancel out. Okay, so let's see how you solve these questions. Okay, so these questions is exactly the same way to solve it. Okay, so I will let you go home and practice this. Okay, so make sure you can practice this one and get the correct answer out. Okay, I want to actually talk about these questions. So here it says, at 250K, delta G not equals to a certain number for this specific reaction. Calculate the value of natural log K. Okay. So keyword here is this and that. Okay, you want to know your natural log K. Okay, the data that you have is delta G not equals to 4.157 as 1000 joules. Okay. Temperature is 250 K. So I hope by now that you've already memorized that how the K and delta G naught are correlated, right? Because previous we keep saying that delta G naught equal to negative RT natural log K, right? So you got this term, you got the T. R in this chapter is always using 8.314. Okay, so you know 4.157 times 1000 equals to negative 8.314 times temperature 250 as your natural log K. Therefore, your natural log K will simply equals to 4.157 times 1000 divided by negative 8.314 times 250. And this will give you a value of negative 2. Okay, so it's actually very simple. If you can just see that the two keywords, natural log K and delta G naught. Okay, so these two will be tied to the delta G naught is equal to negative RT natural log K. Okay, so that's how you solve question number 7. Okay, question number 8. The value of delta G naught for the reaction N2 for this specific reaction is negative 32.9 kilojoules at 298 K. Calculate the value of delta G at that temperature if the partial pressure of N2, H2, NH3 is 0.5, 1, and 2, respectively. Okay, so this is actually a very standard question. Okay, and in these questions, you will always see a feature is that it provides a lot of information on your reaction product. Okay, so every time you see a situation like this, the things you should have in mind is actually it's going to ask you to calculate the Q, the chemical quotient Q. Okay, so every time you see questions, okay, it provides so many information on the reactant products. Okay, think about Q. Okay, so the reason I mentioned this is because so far, that's actually one equation that we talk about has Q in it. Okay, which is actually we talk about the delta G of your reaction equals to your delta G naught minus the delta G, right? Which is natural log RT natural K plus RT natural log Q. That's the only equation that contains Q, and that's the equation you're going to use here. Okay. So the question is actually asking you for the delta G of your reaction. Okay. And then the data you have is delta G naught equals to negative 32.9 as 1000 joules. Temperature is 298 K. Okay. And then you have a bunch of information, right? Pressure of your N2 equals 2.5. Pressure of your H2 equals to 1. Pressure of your NH3 equals 2. Okay, and then the equation you have is N2 plus 3H2 that give you 2 NH3, meaning that you can compute your chemical quotient, which is going to equal the pressure of your NH3 square, pressure of your N2 plus power, pressure of your H2 to the cube, which is going to give you 2 to the second, 1 to the first, sorry, I put it wrong. NH3 is 2. H2 is, N2 is 0.5. 0.5 to the first power, and then one to the third power. Okay, so if you calculate this, then you can get your Q is going to equal a value of 8. Okay, so those are the information, those are the data that you have, right? Then you can actually plug in the delta G of your reaction is going to equals to delta G naught plus RT natural log Q. Delta G naught is negative 32.9 times 1,000 plus R 8.314 T 298 and natural log Q natural log 8, right? So if you do this calculation, you will be able to calculate your delta G of your reaction. Yeah, equals to negative 27748 joule, or become 1, 2, 3, negative 27.748 kilojoule. That's actually how you get to this answer. Okay. So let's actually how you solve question number 8. Okay, so question number 9. Again, it is actually the equation that use the very last concept we say, right? So you have to recalculate the delta G. You need to actually calculate the delta G value. Okay, so if you calculate your delta G value, it's actually negative, then move to the product side. Positive, move to the reaction side. 0 is equilibrium. Okay. So how do you actually do that? Here again, the Q is actually, the question is asking you the reaction direction. Okay. The data, do you see this again? It gives you a whole bunch of information of your reaction and product, right? That means it asks you to calculate the Q again. Okay, so it's the same equation, right? So the pressure of your NH3 square, pressure of your N2 first power, pressure of your H2 to the Q. Right, so NH3 is 21. N2 is 4.2. H2 is actually 1.8. Okay, so if you do that calculation, your Q is going to equal to 18. Okay, and then it tells you the K is 41, right? Because we know the delta G of your reaction equals to delta G0 plus RT natural log Q, right? And delta G0 is negative RT natural log K. So you can further expand this equation. Okay, so you got your Q here, you got your K here. Okay, so you can calculate this is negative 8.314 times 400 times natural log K is 41. Okay, plus R is 8.314, T 400 natural log 18. Okay, so if you do these calculations, you'll end up with, so the first term is negative 12349.86. Second thing is 9612. Okay, so you end up with a value of negative 27370 joule. So your delta G of your reaction is negative. Okay, therefore, it's going to move to the product side, and then the delta G of this is this number. Okay, so that's all right. Yeah, I think that's all. Okay, sorry I got delayed a little bit, but I feel like it's good for us to finish all the questions. Yeah, so let's see. Yes. This question?
I missed the second test. Like, will I email you on that?
Did you?
Yeah. No, I didn't email you yet. Like, I
Okay.
missed the test because I went 5 minutes late. They're telling that I can give the test. And then the next day, there is no like space.
I understand that. Yeah. So you can take the makeup exam, but I will give you 25% penalty for that.
25% penalty. Oh
Yeah.
my God, I don't even have any situation right now. So like,
Yeah. So you will need to do like that. So email me so I can
Yeah.
actually arrange that for you.
it will be like 25% gone.
Yes.
Oh my God. Then I will miss like A, B, C, D, everything because the first exam was not that good, sir.
Yes. So yeah, but that's what it is, right? So that's the rules. That's nothing I can actually change over there. Yeah.
Get it grader then, sir. Please, sir, do something for me, right? Because the first exam that was not that much good for me. I was thinking that if I get good in the second one, then I can at least make near the A.
Yes.
But if I'm like getting 25% down, it's a big huge problem.